let's continue, right. So we are looking at the Bode plot or the Bode diagram, right, and if you recall, like we saw that the Bode plot has two plots, a magnitude plot and a phase plot, and one of the big advantage of plotting the magnitude in decibels is that, like, if we have the transfer function as a product or ratios of individual blocks, right, one could essentially plot the magnitude plot of the individual blocks and then just add them, right. So that was the advantage of having the magnitude plot in decibels, and same story with the phase plot, right. So you have a phase plot, like we just plot the individual factors and then like add them, right. So that's the advantage with the magnitude plot and the phase plot, okay. And the reason why we want to choose the frequency in a logarithmic scale is to essentially cover a wider range. And if you recall, like the basic factors that we looked at were 3, a constant, the derivative term s, and the integral term 1 by s, right. So these are the 3 factors which we have looked at till now, right. So today let's proceed and look at the next factor, okay. So see what numbering did I use there. No. So just to ensure that I am consistent, okay, I used 3, okay. So let's say as the 4th factor, let's say we choose a g of s to be 1 by Ts plus 1, okay. So a first order term, right. So of course we have 1 by Ts plus 1, like, and let's basically consider, of course, t to be greater than 0. We'll see what happens when t becomes negative, okay, later on, right. So to begin with, we'll consider that t is a positive real number, okay. So let's say we have 1 by Ts plus 1 as our factor. So what will happen to g of j omega? Please recall that we are dealing with the sinusoidal transfer function, right. So you substitute s equals j omega. So this is going to become 1 divided by 1 plus j times t omega. So this can be rewritten as 1 minus j t omega divided by 1 plus t squared omega squared, right, when I multiply by the conjugate factor, okay. So this is what is going to happen. So consequently, what will happen to the magnitude of g of j omega? So from this factor, we know that it's going to be the ratio of the individual magnitudes. So I can rewrite this as 1 divided by square root of 1 plus t squared omega squared, right. So that's pretty straightforward. And the phase of g of j omega is going to be minus tan inverse of t omega, right. So that's going to be the magnitude and phase of this particular factor, okay. So one can observe that, like as we go to more slightly complex terms, like the expressions become a little bit more involved, right. So but then we are going to do some simplifications, right. So let's look at the magnitude first, and then we will go to the phase, okay. So this is what we have as the magnitude and phase of this first order term, right. So now let's look at the magnitude term, okay. So we are going to look at this magnitude term, okay. So at low frequencies, when omega is very, very small when compared to 1 by t, we will see why I am choosing 1 by capital T as a particular value, right, in this expression, okay. So when omega is very much lower than 1 by capital T, what do you think is going to happen to this magnitude? So we can immediately see that the magnitude of g of j omega is going to tend to 1, right. Why? Because let's say when omega is less than 1 by t, you can immediately see that t omega is very, very small than compared to 1. Then what can you say about 1 plus t squared omega squared? If t omega is very small, like 1 plus t squared omega squared is going to be even smaller. Let's say t omega is 0.01. What's going to happen to t squared omega squared? It's going to become 10 power minus 4, right. So 1 plus 10 power minus 4, I can approximate it as 1 itself, right. So the magnitude is going to tend to 1 or equivalently 0 decibels, right. In decibel units, it's going to tend to 0 decibels. Do you agree? See, because how do I convert to decibel units? I take the logarithm to the base 10 and multiply by 20, right? Logarithm of 1 is going to be 0, right? So that's why I get 0 decibels, okay? So we would see that the magnitude of the this particular factor is going to tend to a line which corresponds to the 0 decibel line in the magnitude plot as frequencies become smaller and smaller when compared to 1 by capital T, okay? So for this reason, this particular value or locus is going to be denoted as the low frequency asymptote, okay? So this is what is called as a low frequency asymptote. See, why is it called? Because it tends to this value, right, as omega is very, very small at low frequencies, right? Yeah. So that's why the 0 decibel line in the magnitude plot is called as the low frequency asymptote. Now at high frequencies, what do I mean by high frequencies? You know, like when omega is much greater than 1 by t, of course when omega is much greater than 1 by t, what's going to happen to t omega? You can immediately see that t omega is going to be much greater than 1. Then let us say t omega is, let us say 10 power 2, let us say 100, right? T squared omega squared is going to become 10 power 4. So what can you say about 1 plus t squared omega squared? I can say that it's going to be 1 plus 10 power 4, that's almost 10 power 4, right? So I can say that I'm going to approximate 1 plus t squared omega squared as t squared omega squared itself, right? So what's going to happen to this magnitude? So immediately we can observe that the magnitude of g omega tends to 1 by t omega. I hope it's clear how we got this, right? So or in decibel measures, it's going to be minus 20 log to the base 10 t omega decibels, right? Because you take logarithm to the base 10, you will get minus log 10 t omega and multiply by 20, okay? That's how you get this measure, right? So this is the value to which the magnitude will tend to at high frequencies, right? So that's why it's called as a high frequency asymptote, okay? So I hope it's clear what are low frequency and high frequency asymptotes, right? So essentially we are looking at what happens to this magnitude at frequencies lower than 1 by capital T and higher than 1 by capital T. And why did I choose capital T and 1 by capital T here? You know, like please remember for a first order factor 1 by Ts plus 1, right, capital T greater than 0, you know, like if you recall the physical significance of capital T, that was a time constant, right, of a first order system, right? So if you recall a Planck transfer function of the form 1 by capital Ts plus 1, right? Yeah. So why did I consider 1 by capital T? You know, like we can note that the low frequency asymptote and the high frequency asymptote intersected. Where do they intersect? See, please note that, you know, like the high frequency asymptote is going to be a straight line, right, in the Bode plot. Why? Why is it going to be a straight line? Because it is log of omega, log of t omega, of course t is a scalar, right? So we are going to plot omega in a logarithmic scale, right? So when you plot omega in a logarithmic scale and you plot a logarithmic function, that's obviously going to be a straight line, right? So you see that 0 decibel line is a horizontal straight line. The high frequency asymptote has a slope, we will come to the slope shortly, and then essentially that's also a line, straight line, and obviously both of them are going to intersect somewhere, right? So where do they think they are going to intersect? Wherever the high frequency asymptote value will become 0 decibel, right? Where does the high frequency asymptote value become 0 decibel? When t omega is 1 or omega equals 1 by capital T, right? So you can immediately see that when omega equals 1 by capital T, the low frequency asymptote which is 0 decibel and the high frequency asymptote will give the same value, right. So, essentially in principle they are intersecting each other, right. So, this is what is called as a corner frequency, okay, or some people will call it as the break frequency. See, one thing which you should be careful about when you do practical problems is that like all this frequency omega should be in radians per second, okay. So, that is a very common thing where people can make a mistake, because typically we talk about frequency in hertz, right, but when you talk about omega it is going to be 2 pi f, right. So, you need to convert that frequency given in hertz into radians per second, please remember that, okay, when you do practical problems, okay. So, this is essentially what is called as a corner frequency or a break frequency, okay, is it clear? Okay. Now, let's plot them, right. So, essentially, but before we plot, let's ask ourselves the question, right. So, the question that we are going to ask ourselves is that what is the slope of the high frequency asymptote, okay. Okay, let us ask ourselves the question, what should be the slope of the high frequency asymptote, right. So, the high frequency asymptote is going to be minus 20 log to the base 10 t omega, right. So, what is the slope? So, of course, a common way to find the slope is that, like, let us say as we discussed, it is going to be expressed in decibels per decade or decibels per octave. Typically we express in decibels per decade. So, what you do, you choose a particular omega and go to 10 times omega and then find out what is the difference, right. So, that is the whatever is the difference is the value of the slope in decibels per decade, right. So, let us look at that. So, if I go from omega to 10 times omega, let us say from t omega to t times 10 omega. So, what am I going to get? What will happen to this? Here I can rewrite this as minus 20 log to the base 10 minus 20 log to the base 10 t omega, and what is the first term? It is going to be minus 20 and minus 20 log to the base 10 omega, right. Okay. So, what did I do, just to answer this, to be more formal, at a frequency 1 decade above omega, this is going to be this. So, what do you think is the slope? The slope of the high frequency asymptote is going to be minus 20 decibels per decade, right. Why? Because you can see this, right. So, you are going to have a difference of minus 20 from omega to 10 times omega, right. So, consequently, the slope of the high frequency asymptote is minus 20 decibels per decade, okay. That is what we have. Fine, okay. So, that is what we have as the slope of the high frequency asymptote, right. So, of course, what is the slope of the low frequency asymptote? 0, right. It is just a flat line, right, on the in the plot, right, the magnitude plot. So, let us plot these two things, okay. So, let us plot them. So, let us draw the magnitude plot, we will then come to the phase plot, right. So, first let me plot the magnitude plot. So, let us say this is omega, this is magnitude of g of j omega in decibels, right. Let us say this, let us say this I call as 0, okay. Let us say this I call as minus 20, right. So, 20 minus 40 and so on, okay. So, similarly, let us say I take a frequency 1 by capital T, I take a frequency 10 by capital T, and I take a frequency 0.1 by capital T. Like I am just looking at a region 1 decade above and below the corner frequency, right. So, I can do this, I am just plotting 1 by capital T. So, let us plot the low frequency, high frequency and the actual curves, right. So, see the low frequency asymptote which I am indicating in pink, so is the 0 decibel line, right. So, it does not matter what the frequency is, of course it makes sense only at the low frequency, but I am just drawing it, okay. So, just to make the things clear, right. So, the 0 decibel line or the pink line is the low frequency asymptote. Of course, it makes sense only at low frequencies, right, just for the sake of clarity I have just extended it, right. So, what about the high frequency asymptote? The high frequency asymptote once again makes sense only after 1 by capital T. So, how do I draw it? At 1 by capital T the value is 0 decibels, right. At 10 by capital T it is going to be minus 20, right. So, I plot minus 20. So, essentially I draw a straight line which passes through these two points. Okay, so this is the high frequency asymptote. Okay, the one in golden color, right. So this is the high frequency asymptote. Okay, so of course the slope of this line is going to be minus 20 decibels per decade. Okay, that's what we are going to have. Fine. Okay. Now they both of them intersected 1 by capital T. Okay. So for drawing Bode plots by hand, as far as problems in your homework, exams, and are concerned, you need to only plot the asymptotes. Okay, and use the asymptotes curve as your approximation of the Bode plot for that particular factor. So what I am going to draw is the first approximation. Okay. So what is the approximation? I am just going to draw by a solid what to say curve. So let us say, so the approximation of the factor 1 by Ts plus 1 is going to be this. Okay. So it is going to remain 0 decibels till 1 by capital T, and after 1 by capital T it is going to essentially reduce at the rate of minus 20 decibels per decade. So what I have drawn in the maroon solid line is the asymptotic approximation of G of 1 by Ts plus 1, the magnitude of 1 by Ts plus 1, okay, to be very 1 by Tj omega plus 1, okay, that's what I have done, okay, but that's enough for drawing by hand as far as the exams and homeworks are concerned, okay. But what about the real curve, right? So how does it look, right? Because see, this is like basically a non-smooth curve, right? Because why? Although it's continuous, at omega equals 1 by T you suddenly have the slope changing, right? But the real function is a smooth function, right? So it's basically what is the actual magnitude? You can see that that's going to be 1 by 1 plus T squared omega squared, right? So let's figure that one out, right? So how do I do that? So for in that exercise, you know, like please calculate and tell me what values you see. So let's say at omega I am going to construct a table. The actual magnitude in decibels and the asymptote value, okay, in decibels also, okay. So what I want you to do is that, like please calculate at 1 by T, right, and 2 by T, okay, 0.5 by T, okay. So please calculate that these three values and let me know, okay. So can you do that, please? Because it makes sense only after 1 by capital T, right. So yeah, if you want graphically, you know, like a representation, see physically it doesn't make sense, right. See these asymptotes, yeah, let me do it. That's just a, but then you should not treat it as an asymptote it's just a line, right. So please note that the high frequency asymptote makes sense only when omega tends to infinity, right. Similarly, the pink low frequency asymptote makes sense only when omega tends to 0. Here you just look at some two lines which are intersecting, okay, so that I want to provide you with a graphical visualization, right. So yeah, Okay, let's look at. Can you tell me what are the values you get? Yeah.
The asymptotic approximation only makes sense at either extreme, so there will be a huge deviation.
That's what we are. Please calculate. Good point. That's exactly the purpose behind this exercise. Okay. Yeah. Let's see how huge this deviation is. Right. Okay. So what do you think will happen to the value of magnitude of g omega, the actual one, right? So in decibels. See, what is the magnitude of g omega? I think I should scroll up a little bit, or I should scroll down a little bit, right? So yeah, I think so that is visible. Let me erase this. Please note that the actual magnitude of g omega in decibels is going to be minus 20 log to the base 10 square root of 1 plus t square omega square, right? This is as it is, right? No approximation. So now substitute omega equals 1 by capital T there. What do you get? You get log of square root of 2, right? What is that? So that you can say as minus 10 log of 2. What is log of 2? 0.3010, right, to the base 10. So I can say that this is going to be minus 3.01 decibel. And what is the asymptote value? 0, right? So consequently, what is the change? The error, the magnitude of the error is going to be, sorry, minus 3.101 decibel. Okay, difference. Sorry, let me write it clearly. So the difference is going to be minus 3 decibels, right? Do you agree? So obviously between the asymptotic approach and the actual curve, you are going to have minus 3 decibels. So the idea is that, like, if you want to be very particular, you can apply this correction. See, please remember, see, why am I doing all these things? Suppose, let's imagine that we don't have a computer, right? We don't have access to a computer. You need to draw by hand and do control design and take some calls, right? So you can follow this approach, right? But you should also have an intuitive idea, right? See, someone, let's say tomorrow I give you a Bode diagram, and then I ask you to figure out the transfer function, right? So if you know these concepts, you would be able to hypothesize what should be the potential transfer function, right? So that's also another objective why we are doing these exercises, right? So now calculate at 2 by t. What's 2 by t when compared to 1 by t? 1 octave, right? Beyond the corner frequency, right? So can you calculate what is going to be magnitude of g omega in decibel? So you substitute and then, like, you get square root of 5, right? So what is minus 10 log of 5? Can someone calculate and tell me? Do you have a calculator? No. So log of 5 is 0.69, yeah, right? So then I multiply by 10, I'm going to get minus 6 let's say 99, right? So I think it's going to be close to minus 7, right? So but anyway, I will write this value, it's going to be minus 6 let's say 99, let me round it off, right? Decibels, okay? So what is the asymptote value? Where will you substitute for the asymptote value? You will substitute in the high frequency asymptote. Why? Because now the omega is greater than the corner frequency. So I can't say asymptote value is 0 decibels. I have to use the high frequency asymptote. What is high frequency asymptote? It's minus 20 log t omega. So you substitute omega equals 2 by capital T in that, what are you going to get? You are going to get minus 20 log 2, right? Because please recall, the high frequency asymptote is going to be minus 20 log t omega in decibels, right, for the high frequency asymptote. So when you substitute omega equals 2 by capital T, you get minus 20 log 2, right? So what is minus 20 log 2? Let's quickly calculate that, right? So although it's going to be pretty straightforward, but let's do that, right? So I'm going to get 0.3010, right? Multiply by 20, you get almost around 6, right? So we are going to get around like 6.6 0.02 decibels, right. So, so this is going to be minus 6.02. So, what do you think is the difference between the two? It is going to be 0.97 decibels, right. So, now can you calculate at 0.5 by T? Can you calculate at what happens to the actual value at 0.5 by T? So, if you have to plug in that equation, so T squared omega squared is going to be 0.25, right. So, you take the square root of 1.25, okay, and then multiply it by, oh no, wait a minute. So, essentially we have 1.25 square root, then you take the logarithm, right, and then multiply it by 20. That is what I am doing. So, I get 0.97, right, minus 0.97, okay. So, what will be the asymptotic value at 0.5 by capital T? 0. So, what is the difference? The green color indicates the difference, right, between the actual one and the asymptote one, right. It is going to be 0.97 decibels, right. So, now you can complete the same exercise, right. Let us say you do 10 by T and 0.1 by T, right. So, what are you going to get at 10 by T as the actual value? You plug here. So, you are going to get T omega to be 10. So, T squared omega squared will be 100. So, you take the square root of 101, right. So, take the square root of 101, take the log and then multiply it by 20. So, you get minus 20.04. Am I correct? So, this will be minus 20.04. And what will be the asymptotic value? Minus 20. So, what is the difference? Minus 0.04 decibels. So, and what about at 0.1 by T? So, T omega becomes 0.1. So, you need to take square root of 1.01, right, and then like take the logarithm of that and then multiply it by 20. So, once again you are going to get minus 0.04, right. So, and then what is the asymptotic value? 0. So, what is the difference? Minus 0.04 decibels, right. So, you can see that this is the level to which the asymptote and the actual curve will differ from each other, right. So, essentially you can see that you are going to get the maximum error at the corner frequency, and then the errors are going to just decrease. So, if you plot the error versus omega, so this is the error in decibels, okay. So, what is going to happen is that, so if you have 1 by capital T, 10 by capital T and minus, sorry not minus, 0.1 by capital T, what is going to happen is that, so let us say this is minus 3.01, right. So, you are going to have the maximum error here. Beyond that, like you are going to have on either side a decreasing error profile, right, which will asymptotically tend to 0, right. That is what you are going to have as far as the difference is concerned, right. So, yes, the drawing the asymptotes is only an approximation, but a reasonable approximation, right. So, you are going to get a maximum error of 3 decibels, right, in magnitude, but that is okay, like one can, if we are very particular, let us say imagine a case where people did not have any computers, right, let us say a century ago, correct, and you wanted to create the Bode diagram, right. Let us say you take a piece of paper and you can apply these corrections and then draw a smooth curve, right. So, that's still okay, like that is the best we could do, right. So, that essentially takes care of the magnitude plot, right. Is it clear? Any questions? Okay.